This tutorial is about numerical integration using trapezoidal rule, and compared to the rectangular method where we were summing up many rectangles, in this case we sum up many trapezoids. So basically, in terms of Newton-Cotes approach, instead of treating the value of the function in each interval as a constant, we treat the value of the function as a straight line, which has both intercept and slope. So we have two degrees of freedom, and it basically turns out to be the area under a trapezoid instead of area under a rectangle. So in order to implement this, the overall model of the code is very similar to the rectangular model. The only thing we change is when we run this loop portion, and so you can save as your rectangular code and then change some minor changes here to make it a trapezoidal code. So again, most of the portion is the same up to this point. We'll just copy paste that, and you can see that instead of the stairs function that I used in the last one, I'm just using the plot function so that you can see the trapezoids. And now we implement the multiple applications of trapezoidal rule, which is the second line, and it's basically delta x over 2 times this sum, where the function value at the beginning and the end is summed once, and then everywhere else it's summed twice. And that's basically what's happening in this little code. We start by saying that the numerical integral value is the first value plus the last value, and then all the intermediate values from 2 to n minus 1 are added by multiplying them by 2, and then after the loop ends we multiply dx by 2 to which is this delta x over 2 portion of the equation, and then we print the results. So when we run this code, you see that it's 173.33 and 172 is our numerical result. Actually, we should also print, do that for the previous code as well. Find out the error, which is, you can add IA minus IN in the display command, so you can see how much error you're getting in the integral. And in a similar manner, now let's reduce the dx size, and you can see how it will get to the exact result much faster or closer than the rectangular method, which had more error.